Figure 2 shows a cylindrical tank of height 1.5 meters, and initially the tank is full of water. Just going to write that down mathematically. So that means when t is equal to 0, capital H, that's defined a little bit later on, is equal to 1.5. And the water starts to leak from a small hole at point L in the side of the tank. So it's going to be coming out, and then while the tank is leaking, the depth H of the water in the tank is modeled by this differential equation. And we're asked to show that H can be written like this. Okay, so let's integrate this differential equation. It has just a function of t on the right-hand side, so I don't need to do separation of variables or anything. I can simply integrate the right-hand side to get t. Let me actually write it up here. So h is going to be the integral of minus 0.12 e to the minus 0.2t with respect to t. So when I integrate an exponential, I'm going to get the same thing, but we're sort of doing reverse chain rule here. I'm just going to be dividing by minus 0.2. E to the kt integrated is going to be 1 over k e to the kt, because when you differentiate, you times by the k. So I'm going to divide by minus 0.2, which is actually the same as timesing by minus 0.5. And this gives 0.6 e to the minus 0.2t plus an arbitrary constant c. This is where I'll bring in that earlier constant. When t is 0, h is 1.5. So I can say that 1.5 is going to equal 0.6 times e to the 0. Actually, that is just 1 plus c. So c is going to be 0.9. And therefore h is 0.6 e to the minus 0.2t plus 0.9. Find the time taken for the depth to decrease to 1.2 meters, giving our answer in hours and minutes to the nearest minute. So I can set h equal to 1.2, sub in. So 1.2 is going to be 0.6 e to the minus 0.2 t for this specific time now, plus 0.9. I can minus 0.9 from both sides and then divide by 0.6. That's going to give me 0.5 equals e to the minus 0.2t. And we're ready to take logarithms. So, or I can just basically undo the exponential. I'm going to get minus 0.2t is equal to ln of 0.5. That's our log to base e, which means t is going to be ln 0.5 divided by minus 0.2. But again, I can write it as minus 5 ln 0.5. And at this point, I'll put it into my calculator. So minus 5 times ln, it's got to remember where it is. Here it is, shift log 0.5. So I'm using this an app for this like new ClassWiz calculator. I'm so used to using like the original one that I can't always find the right buttons. But here we go, 3.4657. So that's 3 hours and just under half an hour. But to figure out exactly how many minutes, I'm going to minus 3 and then times through by 60, because that's what I just had there, the 0.4657. That was the number of hours less than 1. And so, yeah, times by 60, I get the number of minutes. So 27.944. Rounded to the nearest minute is 3 hours and 28 minutes. That was B. Well done. Finally, in the long term, the water level in the tank falls to the same height as the hole. Find, according to the model, the height of the hole from the bottom of the tank. So we need to think about what's going to happen as t becomes large. In fact, we're going to let t approach infinity. Then an exponential, this negative exponential here, e to the minus 0.2t, that's actually going to approach 0. So h is therefore going to approach 0.9. And that is going to be the height of the hole from the bottom. So 0.9 meters is our answer. We could, just for fun, sketch this function out, and of course it can give us insight into it. Um, so I'm going to build it up. So I know that my normal exponential looks like this. If I put a minus in front, then it becomes a negative exponential. It looks a bit like this. If I times through by zero point 0.6, it would be a stretch in the y direction. It would go through the y-axis, or in fact the h-axis in this case at zero point 0.6 now. And then if I add 0.9, then it translates it in the y direction by that 0 0.9, which means the asymptote, which was at h equals 0, becomes h equals 0 0.9. And that's what it's going to look like. Remember when t was 0, oh, we've now added 0 0.9, so this is going to be 1.5. So that is a rough little, and there is no negative sign, but that is roughly what is going to be happening here. It's not, okay, it's probably going to be, it's not like greatly to scale. I'd probably draw it like that if I had to do it again. But yeah, it's just going to decrease exponentially down to 0 0.9, and then it's gonna like, it's never going to reach 0 0.9 technically. It's just going to like tend towards it. In reality, of course, it is going to hit that 0 0.9, but this is a modeling situation. Um, and yeah, that's it. Well done.